All right, so here's what I'm going to try to do. I haven't done this in a while. Brings back the days of COVID. I'm going to show you the problems and I want to go through them. Now, these are out of the prior text that they use at Cooper and McElman. And I'm going to share the screen if I can. Can you all see something that has 2.61?
Yes.
Yes, sir.
All right, now that's the problem I'm going to do. I'm going to do it on the laptop or do it on the overhead. But you all have access to these, just so you know. I mean,
Yes, sir.
I think you do. Okay, document camera. It is okay. Now, so we're going to start with 2.61. We did this one, right? 2.61 class. Do you remember? We can do it again real fast if you want, but do you remember for the mean on this one? How many remember doing it? Either say yes or something, indicate show of hands. I think you can raise hand or something in a thumbs up. Pardon me, 2-6.1. Whole idea is they give you the standard deviation. No, I'm sorry, variance of 4 amps. And it says it's a Gaussian distribution through a resistance of 3 ohms. And we did this one. We're going to do it kind of quick just to make sure everybody understand it. So here's a resistor of R equals 3 ohms. This is a Gaussian distribution for I of T. So the actual distribution, I like to draw these to give you a visual. This is for the current. So this would be F of I here. It's going to be Gaussian like this. And it has a 0 mean. And this is the value. This is the probability density function. This is the value of I. So the mean value of I is 0. And they give you that sigma. Now they want to know if it's passed through that resistor, find the mean value of the power dissipated through it. And this is kind of straightforward. Power, right, is equal to I squared R in a simple sense. Do y'all follow me, class? If we want the mean value of this would be the expected value. I think I use W as the symbol because the book's answers do. If you want the expected value of W or P, it's the expected value of I squared R. Since R is a constant, and tell me if you can't see, for this one, you can see it's really, since R is a constant, it's just R times the expected value of I squared. Well, if it's a 0 mean, right, this is really the this is the variance, isn't it? If the mean is 0, if you think about this, sigma of I squared would be the actual expected value of the square of I minus the mean value squared. And if this is 0, the standard deviation is the actual, the variance is the second moment. So that's just going to be R times sigma squared of I. And that would be 3 times, and that would be 4. Did they say variance? No, it says variance is 4. So this is going to be 3 times 4. Or it's 12 watts. And I think that's in the book. Do y'all remember this class quickly? Trying to get through this fast, right? Okay, what's the next part? It says find the mean value of the power dissipated, find the variance. So now we want the variance in the actual power dissipated. Do y'all remember how to get that? Well, that's the mean value, right? Now, if we're talking about this, I'm going to try to, the way I showed it, I think, was this way. If you think about this is current and then this is F of I, which I drew up here. That's got this. Then, because this right here is the case. Hold on for 1 second. When I take a look, before we get into that, when I take a look at the actual, I guess I can just, before I was going to go through the probability business here because the power is I squared R. We look at 2 different regions here for the probability of these events occurring for a given power probability. But instead of that, since it asks for the variance of the power dissipated, so what we want is the expected value of the power dissipated. So it's really the expected value of I squared R minus the mean value squared of the power, which is 12, and I'll just put minus 12 squared. Excuse me, I'm doing it wrong. It should be the expected value of, I'll just write it down this way, of W minus W bar squared. And that would be equal to sigma W squared plus the mean value squared. Oh, I'm sorry. Doing this wrong again. Let's try that again. The expected value of, we've got that one. This is the expected value of I squared R squared. And that would be equal to the expected, or it would be R squared times the expected value of I to the fourth we did this one, and that was, so I'm just going to tell you this. Since for this one right here, this part of it, and let me just try to focus this a little more. I hope this is the last thing I'm going to have to do. I'm not sure I can do anything about that, but I can do this. So that's zero mean. I mean, I has a zero mean. So this is really going to be equal to R squared here. And this is just going to be sigma of I to the fourth power, because the mean value here is 0. And that will be equal to sigma W squared plus omega squared. And that means it's going to be and that should be, somebody just put something in the chat that it will not allow you to unmute. No, I didn't do that, but let me see about this. So this is going to be right here. Should be 288. Didn't we did this last time, right? Class?
Yes, we did that problem in class.
I'm sorry if I'm not going through this as clearly as I should. That's 2.61, 2.62 we didn't do, and I want to do it here. I think y'all know what it is, right? I mean, I can show you the screen, but 2.62 is just going to be, so there's a random variable X is Gaussian with zero mean. So here, and let me know if you can't see something, 2-6.2. Here you have a random variable X, Gaussian, and it's got a variance of 1. Another random variable Y, this is a good one, Y is equal to X cubed. Has anybody tried this problem? I mean, I posted the solutions. Did anybody try it at all? Anybody at all? Or well, how do you do this one? This is Gaussian, right? Mm-hmm. Now, hear me on this one. You need to hear me, because this is going to be something you're required to know. So if that's a Gaussian random variable, keep this in mind. This is an odd moment, right? Not an even, it's odd, right? And you'll notice the mean is 0. Now, with Gaussian random variables, the expected value, if it's got a 0 mean, the expected, or actually even without a 0 mean, the expected value of X to the N is 0 for N odd. How many remember that? Anybody? So I got a few people on the top I can see, and okay, I got a thumb up from Trent. I appreciate it. It does help just get a little feedback, and I thank you for your thumbs up then. So that's N odd. Now, if N is even, right? N is even here. I'm going to put N even, but it has to have a 0 mean. So that means the mean value has to be 0, or this won't work. Do you all remember that it's 1 times 3 times 5 times ... times N minus 1 times sigma to the N? Do you all remember that one for the mean? I mean, for the moment here? How many do? Anybody? All right, that's one you need to know. Hint, this is one you need to know. You can do it on your calculators, and it'll give you the right answer every time. But it takes a little time to do that if you know that. So for this one, the first thing is write the probability density function for y. Well, we'll do that first part in a second, but what's the mean value of y? Look at this. That's y, right? What's the expected value of that? That's the expected value of x cubed, right? Y'all agree with that, class? That's odd, isn't it? That's 0, no brainer, right? If you know it, you got it. I mean, if you know the concept. So that's 0. Next thing, this is part C, find the variance. How do we find the variance of this? Y itself is x cubed, right? That's an odd function. Do you all agree with that? Now, if we just wrote this down, I'll do it fast. If you look at the actual density function for y and f of y here, it's Gaussian, it's a 0 mean, and I'm trying to show you this. This would be 0. F of y itself of y, you don't have to write this down, just follow me, would be 1 over square root of 2 pi, right? It's got a standard deviation, or I'm sorry, a variance of 1, so it'd be 1 over here times exp, and it would just be minus y squared over 2. That's it. Now that's an even function. When I take the expected value, find the variance of y, we know that the mean value of y will be 0, and that's obvious, right? The mean value, if this is even here, and you take a look at this, that means y, the expected value of just y would be 0, or that would be y bar. Then I know the expected value of y minus y bar squared is really going to be equal to the expected value of y squared. I hope you follow me on this, right? And this is all, I mean, sort of, sorry. I'm doing this in a way that I think I'm confusing you. So he asked for the variance of y. Since y is equal to x cubed, the variance of y, and I'll put it sigma of y here, squared, would be the expected value of y minus y bar squared, which is the expected value of, and this is going to be x cubed minus x cubed bar squared since it's 0 mean here, this is 0 mean, this is going to be simply, and it's even, it's the expected value of x to the 6th. That's what I'm trying to say here. And that's even, that's 1 times 3 times 5 times, and it's n minus 1, so this is going to be 5. 1 times 3 times 5 times sigma to the 6th power. So it's 1 times 3 times 5 times 1 to the 6 is just 1, and that's 15. It is the expected value of y squared, and since y is x cubed, it's the expected value of x to the 6th. Since x has a 0, I mean, the value of x has a 0 mean, it's really going to be an even value, and because it's Gaussian, it's just going to be this formula right here, where n even. And I'm sorry I didn't say that a little clearer. Do y'all follow me how I got that, or why it's true? You with me on this? Because really, when we're talking about y equals x cubed, the expected value of y would be x to the 6th, the expected value of x to the 6th, and x has a 0 mean. That's why you can get away with this. Okay, I'm going to go to the next one. Try to go a little faster. 6.3. Did we do 6.3? We're going to do it again real quick, just to be for consistency. I hope you don't mind. 2-6.3 right here, and it says in the book that a current has a Rayleigh probability density function is passed through a resistor of 2 pi ohms. And so here we have a current that's strict positive going through a resistor R equals 2 pi ohms. That's the current. Now this is the Rayleigh mean. Here he says the mean value of this Rayleigh current is equal to 2 amps. And it says find the mean value of the power dissipated. So before I get going on this, this is a Rayleigh distribution mean, right? And I'm going to put it down here. This is Rayleigh. All right. Now, for a Rayleigh distribution, if this is the mean of the Rayleigh, that is not the mean of the Gaussian random variable that the Rayleigh's derived from. The actual Rayleigh mean is equal to the square root of pi. And I'm trying to think of where this is in the book, but sigma, and let me see if I can find that. I'm not sure where this is in the book, but this is the Rayleigh mean. Now, we need this, though. We need the Gaussian mean to continue on. So really, the I bar here is the Rayleigh mean is equal to square root, and we did this in class too, I think, times sigma, which is equal to 2. That means sigma itself is equal to 2 times square root of 2 over pi, whatever that is. So that is the actual, this is for the Gaussian distribution that the Rayleigh is derived from. Y'all with me, class? Are you with me on this one?
Yes.
Okay, just making sure. We did this one. I'm not even going to do that calculation. Now, after that, it says, find the mean value of the power dissipated by the resistor. Okay, so if we have a resistor power, and I'm going to use P, power is I squared R. So if you talk about the expected value of the power, what you're really talking about is R times the expected value of I squared. This is Rayleigh, correct, class? That's a Ray. I mean, the current is Rayleigh. Has a Rayleigh distribution. If I was to draw that, it would look like this. This would be 0, and this would be I in this direction. It would look something like this. There's some other good problems coming in a second. So if we take a look at this one, we want the expected value of I squared. It's going to be non-zero for sure, right here. And that is what? R times, we could write it down directly, but it would be times the actual variance of the Rayleigh current plus the mean value of the Rayleigh current squared times R. That's one way to do it. We could do it directly from the statistics and just take this I squared and multiply it by the density function, Rayleigh distribution. By the way, this Rayleigh distribution right here has F of I equal to simply sigma, and that's the Gaussian sigma here. I'm sorry. It would be I here over sigma squared times exp to the minus, and maybe I should use capital I, minus I squared over 2 sigma squared. And that would be the density function I'm trying to show here. When I is 0, it's 0. I don't have relative maximum. So that's the density function. If we want the value of I squared, you could take this, multiply it by I squared, and you'd get this. And I think I put this up here. Yeah, I put it up here. So the expected value before of, if we're in Rayleigh distribution of the second moment is just 2 sigma squared. I hope you remember that, but that's the Gaussian sigma that the Rayleigh is derived from. Do y'all remember that, class? Just how many do? All right. Now, do you remember what it is, by the way, for the Maxwell-Boltzmann or the Maxwellian? I'm just going to do it over here. What's the expected value if this was a Maxwell-Boltzmann? I mean, second moment of the Maxwell-Boltzmann. It's important you at least appreciate this. Do y'all remember? It would be 3 sigma squared. I don't know if I covered that last time. I thought I did in my notes, but does anybody remember that at all?
Yes, we talked about that like towards the end of the class.
Yeah.
Maxwell
Okay.
Boltzmann.
All right, good. And try to get something that draws a little sharper. So for R's, we know that the expected value of the current, this should run downstairs with some different market. The expected value of, of the actual of R times I squared is actually going to, I'm going to get a different marker in a second, is actually going to be R times the expected value of I squared, and that's just going to be R times 2 sigma squared. So that's going to be 2 pi. And times 2. And then sigma squared is pi over 2, going to be 2 square root of 2 over pi squared, and that is equal to, this is so 4 times 4 is 16 pi, 16 then times 2 over pi, so that's 32 watts, and I think that's yeah, that's 32 watts. Part B.
While he's going to get that marker, I'll just let everybody know that except for today's video, all the class videos besides today is on the website. So if y'all need to go back and look at any of them before the quiz on Friday, they're all up there, and I'm going to try to get this one up today as well.
When I finish this one, let's take care of that test business. You know, this is a rather unsatisfactory way of doing business. So that's 32 watts. The next part of that problem. I mean, any questions about this before I continue, guys? Or if you are, just unmute yourself and tell me. And then the next part of that problem, which we did, was find the probability that the dissipated power is less than or equal to 12 watts. Now, this is the kind of problem I would give you. Here, this is the kind of problem I will ask you. Okay, so, all right, find the probability that the power is less than or equal to 12 watts. So the power, or that I squared R, is less than or equal to 12 watts. Do y'all remember what I said to do on this one? Current is Rayleigh, right? Rayleigh has, it starts at 0 and it's positive, right? So if we take a look at this, if the probability that this occurs is really that what? I squared R less than or equal to 12, less than or equal to 12 divided by R equals I squared. It's the probability that I less than or equal to what? Square root of 12 over R, right? And that's equal to the square root of 12 over 2 pi, or square root of 6 over pi. Do y'all agree with this? I mean, y'all follow me on what I'm doing here? What I'm doing? Okay, I got one thumb up. I'm assuming if there is a problem, just tell me. So if we want this, and again, this is problem 2-6.3, and this is part B. Since we already did this one, it shouldn't be too bad. So it's really the integral of the Rayleigh distribution function, which is going to be, I'll just say this, that for a Rayleigh distribution, the probability of anything x being less than or equal to a is really 1 minus exp to the minus a squared over 2 sigma squared. But take note, that sigma is the Gaussian sigma that the Rayleigh is derived from. That's the one mistake you're going to make. People put the Rayleigh sigma in there. Is everybody following me on this? That's the standard deviation associated with the Gaussian. It's so important to realize this is derived from Gaussian, and so is the Maxwell-Boltzmann. Now, we do have that value. I happen to turn the page and I forgot exactly what it is, but I mean, this itself, this times square root of pi over 2 is the Rayleigh, so square root of 2 over pi. Well, we have it down on the page before. I'm just going to not even bother with that right now. Now, that's the probability. So that means the probability of I being less than, or really I itself being less than or equal to the square root of 6 over pi here is equal to 1 minus exp, and it would be minus, that's going to be squared, so it's going to be 6 over pi over 2, and what was that sigma value? 2 square root of 2 pi. So the value of sigma was 2 square root of 2 over pi, and this is, of course, at the Gaussian one, so that's going to be, if I square that, I'm going to get 4 times 2 over pi. The pi's cancel, and I get this. That's 1 minus exp to the, what is that? Minus 6 over 16, is that right, class? I think. And I think that's what I had, 0.03127. I think we got that in class too. And so that's that probability. Finally, the one, and I got a question for you after this. They asked for the probability of it being over 72 watts, right? So then they asked part C of this one is they want the probability of the power being greater than 72 watts. So again, I do it this way. If that's, instead of getting a probability density function for power, you could, but it makes no sense to do it if you got a Rayleigh already. I know since power itself is I squared R, the value of I it has to be greater than would be equal to, I would take P over R and take the square root. So it'd be a square root of 72 over R, which is 2 pi. And that means I greater than or equal to square root of 36 over pi, whatever that is. Now, just leaving it like that, if it's greater than this, so the probability that the power is greater than 72 would be equal to 1 minus, and then technically it would be 1 minus exp of minus this value of I squared over 2 sigma squared. That's what it is technically. Y'all follow me? I'm just writing down the actual mathematical formula, but you can see the ones cancel. You all see that 1 minus 1 is 0, and then the minus sign right here becomes a plus. So it's just equal to exp of minus I squared, which would be 36 over pi, over 2, and then sigma is going to be, sigma squared is 4 times 2 is going to be 8 over pi. And the pi's cancels. All right, so that's equal to exp of minus, and the pi's cancel. I get 36 over 16. We did this one, but that is, somebody's math kid to do that. I'm getting 0.015, 105. My answer. That's what we got, 10.1054, I think is the solutions, right?
Yes, that's what we had on Wednesday or on Monday in class.
I'm sorry, I'm going through this again. I'm doing it basically to do this sequential because you're going to see a chi-squared distribution is what a lot of this stuff can be derived from. For any order, they call it degrees of freedom. Like the power problem had 1 degree of freedom. We're going to see the Rayleigh had 2 degrees. Remember, the arrow could land in an X and Y deviation from the center. That's called 2 degrees of freedom. The Maxwell-Boltzmann has 3 degrees of freedom. And you're going to see all these things can be derived directly from something called the chi-square distribution. I have a lot of notes about this. It's very awkward for me to do this here. I prefer a board, but I'm going to try to do it anyway. So next, the next problem on topic is, and I can understand why you probably didn't do them, but all right, this is one we didn't do. This is a good one. Did anybody try this problem at all before just looking at the solutions? This is a good problem. All right, well, see how you can, tell me how you do it. If anybody's got a suggestion, please just unmute. It's not a hard problem, and it falls right into the lap of the Rayleigh. So it says marbles, this is 2-6.4. Here we're dealing with rolling marbles on a flat surface have components of velocity that are orthogonal. It's only 2 dimensions. It's got 2 degrees of freedom. It can be X or Y, think of it that way. That are independent Gaussian random variables, which is nice, and having 0 mean, which is ideal. So Vx is equal to Vy, and the mean of that is 0. That's a godsend. When mean's 0, a lot of things get real easy with Gaussian random variables. All right, so for that, it also says, now pay attention to this one. There's 2 things in here that are very important. First thing they say is find the most probable speed. This is important. So they're looking for the most probable speed. And here's what they mean by that. Please listen to this. You're going to be tested on it. This is 0, and this is the value of the magnitude of V. Here, the magnitude of V is equal to the square root of Vx squared plus Vy squared. Just like the arrow's standard deviation from the target. If it hit X and Y at that point, and the center was 0, then the distance from the target center r would be the square root of x squared plus y squared. Here it's a velocity. So the velocity looks like this, something like this for a Rayleigh distribution. This would be f of r of v. That's v magnitude now. Now f of r of v, you got to kind of know this. That's equal to v over sigma squared. That sigma is the Gaussian sigma that this thing's derived from, the two Gaussians. So important to remember that. You might even want to put a sub g there to remind yourself it's Gaussian times exp to the minus, and it's v squared, it's magnitude v squared over 2 sigma squared. Here again, Gaussian. Everybody with me, class? Now, it says in the problem statement that the Gaussian random variables, the x and y velocity, have a 0 mean. That's a godsend. If it's 0 mean, it's great. If they have 0 mean for a Gaussian random variable, and what is it? It says, and a standard deviation of 4. So then they say, this is the Gaussian standard deviation is equal to 4. And that means sigma squared is 16. Now, hear me now. You all see how that's the density function, probability density function, right? The most probable value is the peak value of this. We're looking for this. The peak value right here is the most probable value. Y'all with me? How do you always get the peak or the minimum of any function in any dimensions, but say one dimension? I mean, 2 dimensions. Say y versus x, you want peak of y. Class?
Do you find the derivative of the function and then set that equal to 0?
And that is the answer. You're going to use that concept over and over again. All right. If it was something, a surface, you would take the gradient of the surface vector and set it equal to 0, which would be the local minimum. If it was 3 dimensions, same deal, but it's the minimum is always by derivative. So for this one, what we're going to do is take a derivative of this, and he does this, I think, of f of r of v dv and set it equal to 0. Now, I'm going to go ahead and do it here, and I hope you can all see me, but just do it by yourself. If I take a derivative of this, I'm going to take the derivative of the first, which is just 1 over sigma squared, times the second, which is exp to the minus v squared over 2 sigma squared. Then it's going to be plus the first, which is going to be v over sigma squared. You can do it a couple different ways, times the derivative of the second. Now that's a derivative of the argument inside that exponential. Can you all see this, class? The derivative of the argument with respect to v brings out a what? Minus 2v, right, over 2 sigma squared. And then it's got the exponential again. I'm a little crowded here, but y'all follow me. I just rewrote that term here, correct? Just take a moment. Can y'all see this? Y'all with me? When I take a derivative of this and I get this, I want you to notice something. I can multiply since it's equal to 0, everything, and get rid of sigma. Then I can divide everything by this exponential, get rid of the exponential right here and here. Now I have this, which will be 1, trying to do this right, 1 plus, really, it's 1 minus, and this is going to be what? V squared over sigma squared is equal to 0. And you see how v is going to be equal to, or v squared is equal to sigma squared, or v itself is just equal to sigma. That is the most probable value, the velocity for this problem. And it's really for a 2-dimensional problem like that. Y'all with me, class? That's this value right here, the peak value. Anyway, that's the most probable value. The mean value of the speed is going to be what? We want what? The expected value of v, it's Rayleigh. What is that always? What is it? Square root of pi over 2 times sigma. Isn't that right, guys? All right, but that's the Gaussian sigma, right? So that's going to be equal to square root of pi over 2. And the Gaussian sigma was 4, right? So the most probable velocity, or sorry, this would be just v. The most probable velocity would be square root of pi times 4. And what is that going to be equal to? I got math kids somewhere. There it is. Pi over 2 times 4 equals, I think it's 5.013 I'm getting. I'm not sure what the book has, but I think I got it right. Yeah. Then finally, in part C of that problem, they asked for what's the probability that the marble's velocity is greater than 10 feet per second. So this is part C. And they want the probability of V being greater than 10 feet per second. Now, how do we get that? It's Rayleigh. In a Rayleigh distribution, now please make sure you know this. I know some of this seems a little dry, but you have to know this. And this is only for Rayleigh, but when you take a look at the probability of anything of R being less than A, that's 1 minus the exponential of minus A squared over 2 sigma squared. Now that sigma is Gaussian, A is just a value. As A goes to infinity, the probability is 1. The probability of the event occurring, in other words, has to be 1. So the probability of being greater than A is 1 minus this, which will just be the exponential. So this means it's just exp to the minus, in our case, it's going to be 10 squared over 2 sigma, and sigma has to be the Gaussian sigma squared. It's 2 sigma squared, which is going to be 4 squared, or I'll put it down as 4 squared. And that is equal to, I got math cat here. I'm getting 0.092 roughly. Anybody confirm or deny that? You got it? All right, you got it. I think that's right. So for this one, I don't know what he has in the answer, but wait a second. He has, does he have 0.0439? Anybody else seen that? For the solutions? That's wrong.
Well, that's what I'm getting when I plug it into my calculator is 0.0439.
That's also what I got.
All right, so I got, oh, I see what I got wrong. Instead of 32, it's 42. Yeah, now I get that. Sorry. 0. I'm getting 0.0439 now. I'm sorry. I mistyped something over here on math. Okay, so that was 4. Just hang with me. I want to get through these. So now we're into the Maxwell distribution. I need to get to that. It's a 6.5, and then we'll get to the chi-squared and it'll be done. So 6.5, so it's 2-6.5. Now this is the Maxwell-Boltzmann distribution for velocity. Let me just recap. So when we talk about Maxwell-Boltzmann, we're talking about having 3 degrees of freedom, or now the velocity we're talking about is the square root of Vx squared plus Vy squared plus Vz squared. That's if you think about the density function, the f of V for this, if we wanted the probability density of something occurring, it would have a spherical shell equal to the square root of V squared plus Vy squared plus Vx squared plus Vz squared times a differential thickness. That would be the differential volume times the density function. It's different than just f of x dx or f of r dr here. It's different. So when I think about this, first, the density function, we're not going to derive it. I don't think we derived it for the Rayleigh, but you can derive it. It's not too hard. So the velocity function for the Maxwell-Boltzmann, and this is the Maxwell-Boltzmann one. I call it, he just calls it Maxwell. This is a little different. So in his book, it's square root of 2 over pi V squared over, and it's going to be sigma cubed. And then you're going to have the same exponential. I got to make mention. So this is the density function. Just keep that in mind. This is the PDF for the Maxwell-Boltzmann. But I got to say this, and please just hear me when I say this. For this density function, it's assuming the mean value of Vx, Vy, and Vz is 0. Do y'all hear me on that? Now, the reason I'm saying this is I did my master's work in plasmas, and I did a lot of stuff with plasmas and other ionized things. When you have any kind of an electric field that's DC in a plasma, the drift velocity of either X, Y, or Z will not be zero, and this doesn't apply. Then you have to have skewed Boltzmann characteristics. So just remember, if you guys take plasma physics or some of your upper level courses, this applies for standard gases where there's no ionization, you have electric fields present. Do y'all follow me? Just for reference, because you can make a really dumb mistake in this one. Okay, now that's the density function for standard gases. If you take a look at this, the first thing he wants is the variance of the molecular speed. We'll get to that in a second. The most probable, that's the one I want to do. Then we'll talk about the RMS. I'll give you this much. I'm going to put down the variance and the standard deviation. They're just standard formulas. You can go through and calculate it, but trying to figure out where he has it in his book. First of all, if you have a Maxwell-Boltzmann distribution, then when you take a look at the expected value of V for this one, that will be equal to, I'm just writing it down the way he has it. And boy, you can get in trouble if you don't write this down right. This is square root of 8 over pi sigma, but that is the Gaussian sigma, Gaussian standard deviation that the Maxwell-Boltzmann is derived from. So it has to do with the statistics of Fx, Fy, and Fz, or the associated orthogonal components, and it's important. That's the expected value. And then when you talk about the variance of the velocity, and actually, let me do it this way, sorry. When you talk about the expected value of the velocity squared, now this is important. The expected value of velocity squared is just 3 sigma squared. And do yourself a favor, that's Gaussian sigma. And also say it assumes 0 mean values for Vx, Vy, and Vz. If that wasn't the case, you can't do this that way. So the expected value is just 3 sigma squared. Remember, for the Rayleigh, it was 2 sigma squared. Y'all remember that? If the average velocity of the X and Y component are 0. So please just try to appreciate that. Next, now I wanted to get to the part that, so let's just do it. For the variance, what's the variance of the molecular speed? Think about this. That's the expected value of what? Quantity V minus V bar squared, right? That's a second central moment. That's always going to be what? That's V squared bar minus V bar squared. Y'all remember that? So it's going to be the second moment value minus the mean squared, or minus the mean value squared. And what's that going to be? That is 3. You can always get it this way. Sigma squared minus that. And that's up here, and I hope you can see it, right? So when I take that and square it, I get 8 over pi sigma squared. So it's really 3 minus 8 over pi sigma squared, and that's 0.45. I think it's 453, but I don't remember exactly. I've got it down here, 453 sigma squared. And that's the expected, or that's the variance of the Maxwell-Boltzmann velocity distribution, but that's the magnitude. So finally, now for this one, how do we get the most probable value? That's the part. Oh, we might as well get this next part. Part C is, what's the RMS molecular speed, the average? So he's asking for the RMS speed. What he's really talking about is this square root of that. That's all it is. Velocity is in meters per second. This is going to be meters per second squared. Take the square root of that, and you get the RMS speed. So VRMS is just going to be a square root of that, or square root of 0.453 sigma squared, or it's square root of 0.453 times sigma, and that one, I guess it's 253 meters per second. Because the actual value of, what was it? The mean value for this one was, I think, 600. So the average speed was 600. Let me do it this way. V bar was 600. That's the magnitude. And that's equal to 8 square root of 8 over pi sigma That means sigma is equal to 600 times square root of pi over 8. Right here. I come down here. If I do that, I should get 253 meters per second. Anybody confirm that? I think it works out, guys. So anyway, that's that problem. Okay, now how do we get the most probable speed, guys? Just think about that. Think about this distribution. It's similar if you look at it. Just think about it in your head. It's v squared times an exponential. Well, at 0, it's 0, correct, class? And it's asymptotically going to hit a peak. But how do we figure where that peak is, or the most probable value, which is not the mean, by the way. Most probable value is not the mean. And I may have said something in a prior class that was incorrect. The most probable value is the peak value of the density function, the probability density function. It is not the mean value. It can be the mean in some cases, but it's not necessarily the mean. What do we do with this guy? Do you find that, guys? Take the derivative, set it equal to 0. Do you remember? We just did this. Okay. So if we take the derivative and set it equal to 1, now, since I'm going to set this equal to 0 after I'm done, right? I'm referencing this, and I'm trying to make sure it stays in focus. When I take a derivative and set it equal to 0, you see how this constant right there doesn't matter? Y'all see that? And this doesn't matter if I'm going to take a derivative and set it equal to 0. Y'all with me? Got some heavy yawns like, oh, please, please. All right. So what I'm really going to do is take a derivative with respect to v of this, which is just going to be v squared times exp to the minus v squared over 2 sigma squared. That is the Gaussian sigma, and set it equal to 0. When I do that, the derivative of the first becomes 2v times the exponential, right, of minus v squared over 2 sigma squared. Then it's going to be plus that, which is v squared, times the derivative of this, which is going to be minus 2v over 2 sigma squared, because you got to take a derivative of this inside. And then it's going to be times exp to the minus v squared over 2 sigma squared equals 0. Correct, class? Hey, I didn't vote on this test. We're going to do it before you leave in a second, okay? I'm sorry I didn't. Unless, you want to wait till Friday? Because obviously this is not ideal.
Yeah, I think it'd be better at this point just to wait until Friday to vote on it.
I'm sorry I didn't do it earlier, but this is a very unscheduled kind of event. I did not expect to have to do this, but I'm trying to do this. And the term that the university would use out of an abundance of caution, but I just want to make sure everybody's safe, drown going through a stream or something. All right. So if that's 0, the first thing you notice about this, just to make everybody clear, you'll see how that and that appear on both sides. So if we divide everything by it, it goes away. Now, the next thing you're going to see is I really have this equated to this. And I can get rid of the 2v. So I have 1 equal to, forget 2v here, equal to v squared over 2 sigma squared. Y'all with me? Y'all with me? Just take this stuff and rearrange it. You're going to see you get this. Everybody with me? All right. So what's v going to be? Well, v squared is equal to 2 sigma squared, or v is square root of 2 sigma. That is the most probable velocity. Thank you, Trent. I don't see if I see a thumb. Okay, next. I'm out of time, I think, but I'm going to do one last thing. I didn't get to the chi-squared, but I'm going to do it. As a matter of fact, does anybody mind if we postpone the quiz until Monday just because of all this craziness? Okay, on Monday we'll do it.
There's no class on Monday. Next week we're only meeting on Wednesday.
All right, this Friday we settle the exam. Everybody remind me. I tell you, would you mind the quiz on Wednesday for this? Because I want to cover chi-squared and just wrap it up and then show you some more problems.
Yeah, I have no problem with that.
All right, we'll do the quiz Wednesday. I'm very sorry. I hope I don't have to do this again. But if I have to, I'll make sure the camera and everything's ready. This was very offhand. Most of the stuff is not set up for Zoom lectures, so I kind of had to wing it. I'm sorry, guys. Well, I got a bunch of slides I'm going to put up for you guys. Okay. All right, I got a whole bunch of stuff ready for you, ready to take care of this. Today, what I had in mind, I wanted to go to the board, work through these rather quickly, and I wanted to get into the chi distribution, and then also, if we have time, log normal, but show you the application. Now, I don't expect you to memorize everything on this. I will give you the density functions for like Rayleigh. I won't give you a Gaussian, but I'll give you Rayleigh, I'll give you Boltzmann, I'll give you chi-squared, I'll give you log normal. I'll give you the crazy ones. All right. And I'll even give you the variance and means associated with the Gaussian that they're derived from. But you got to know the Gaussian. And I'll give you some more problems that will help make this clear. So please, on Friday, come to class. How about Friday? First thing, and everybody in unison yell at me, vote on the exam. All right. We'll get that done. And then from there, I'll finish it. And then Wednesday, we'll pick up the quiz. Okay. Guys, you got any more questions? I'm hanging out here and I feel bad. I didn't do a better job in this, but do you have any other questions? If you got questions, this is my office hour. Ask away. Anybody?
I do have a question real quick.
Sure.
What is the difference between the mean squared value and RMS?
Well, depends what the mean squared is of. If you have a velocity, let's go back to the Maxwell-Boltzmann one. All right. Did you just jump off? You vanished.
No, I'm here.
Okay. If you think about the Maxwell-Boltzmann distribution, right, for velocity.
Yes, sir.
They're derived from a Gaussian. The Vx, Vy, and Vz are Gaussian. So first thing is when you take the density function right here, that's going to be equal to, this is going to be, and you don't have to know this one, I would give this to you, and it's going to be V squared over sigma cubed exp to the minus V squared. This has got a zero mean though, over 2 sigma squared, and that's Gaussian sigma. So that's the density function. The mean value of this function right here, that's the density function. It starts at 0. It would look like this. It would look something like this. All right. And this is the most probable value right here. That's 0. This would be the velocity here. If you think about the mean value of that, that's just going to be the average value, the expected value of the velocity here, right? You with me? Of that, the expected value of velocity is going to be the thing I put down. It's square root of 8 over pi times sigma. So that's the square root of 8 over pi times sigma. Now, when they talk about the root mean squared value, do you remember RMS currents and stuff like that?
Yes, sir, but I don't recall going into depth of exactly what it was, and I just remembered it, and I wanted to know the correlation between.
All right, let me do this. If you have an AC sine wave for voltage, just assume it's a sine wave like this, and this has a value of say V naught. It's going to be V naught times sine of omega t here.
Yes, sir.
You all know that the average value of this, if this is some V of t, the average value of V of t will be 0. Same above, area above and below, right? Y'all remember this?
Yes, sir.
But what is the RMS value? Well, the RMS, the voltage VRMS is what? Technically,
the square root
of what? 1 over the period, right?
Yeah.
Of what? The integral from 0 to the period of the voltage V of t squared, or a V naught squared sine squared of omega t dt over a period, right? And what's that going to be? Well, if I do this, I'm going to get V naught squared as a constant coming out. Then when I do this, the integral of sine squared over a period is really 1, right? Plus or minus what? It could be 1 minus 2 times cosine of omega t. My point is when you integrate the cosine of omega t over a period, you get 0. So you got 1/2 there. So this becomes, and you got a t here, you're going to have a t there. So you're going to get 1/2. So this is really going to be V naught over the square root of 2 would be VRMS, right?
Yes, sir.
Y'all remember this, guys? The RMS value is not 0 for a sine wave, for an AC voltage. VRMS is not 0, the average value is 0. Now I'm just trying to contrast or compare this to what I'm talking about here. This is the average value here. The average value is not the RMS or root mean squared value. To get that, what do we have to do? Well, it's the root mean squared value. The expected value of the velocity from this distribution right? Squared, right? You got to take that and you got to take the square root of it to get VRMS. When they say
Okay.
root mean squared, you square the operation first, then you take the mean of that squared value, and then you take the square root. That's what RMS means. All right. That's the difference. The mean value can be much different than the RMS value.
Yes, sir.
So RMS, you square it first, then you take the mean of the squared value over any, whatever the period is, over the possible values. Then you take the square root. That's how you always get RMS.
Okay.
And you got to be careful about this too, because your natural gut instinct sometimes is just say, well, take this and square it. That's what people do. Take the velocity, average velocity, and square it. Or take that as the, I'm sorry, take that value as the RMS. It's not. It's got to be this. Is that clear? Anybody else got questions? That's a good one too, because that's mistakes are made there. I know we've got that book, and I could do problems out of it. The problems in that book related to this get fairly involved. Just one of them takes a little while. And I'm trying to just show you the concepts without getting bogged down in all the numerical details of integrations and derivatives. Because I mean, these derivatives are fairly straightforward, but when you get something where you got functions here and you got like 2 or 3 different variables, this is the multivariable thing he talks about there, it gets time consuming. And I got PowerPoints for you. Any other questions? I'm going to put everything up. You can hang on if you want, but I'm going to start putting it up. If you got questions, ask.